So let's go ahead and look at a graphing example here that involves logarithm functions. So we have the function f of x is natural log x squared plus 4. And we first want to know what's the domain of that. Well, remember that you can't put negatives inside a log function, so we need the inside of the log function here, x squared plus 4 right there, to be greater than 0. Well, if you bring the 4 over as a negative, that's just saying x squared is greater than negative 4, but that's true for all x. So our domain is going to be negative infinity to infinity. Well, what about intercepts? Well, remember your x-intercept is the x-coordinate when y is equal to 0. So we're going to set our f of x here, or y, equal to 0. So 0 is equal to natural log x squared plus 4. Okay, and that happens when the inside is equal to 1. So we took that x squared plus 4 right here, set it equal 1. But if you brought that 4 over, that'd be x squared equals negative 3. That's got no solution here. So there's going to be no x-intercept. Y-intercept is the y-coordinate when x is equal to 0. So we just plug in x equals 0 right here. So that's log of 0 squared plus 4, natural log of 4, which is about 1.39 on your calculator. So our x-intercept here is going to be, x-intercept point will be 0, 1.39. Asymptotes, vertical asymptotes, there's not going to be any, because remember with the natural log function, ln of x looks like this, and its vertical asymptote happens at the y-axis, which is x equals 0. So it happens when the inside of the graph, inside of the log function is equal to 0, but this x squared plus 4 is never equal to 0. So our x squared plus 4 never approaches 0. The smallest it can be is 4. So no vertical asymptotes. For horizontal asymptotes, you look at the limits as x goes to plus or minus infinity. Since x is squared, those are both going to be the same. If x goes to infinity, x squared does, and so does x squared plus 4. So your x is going out to infinity, your log function goes up to infinity. So that's this one. So no horizontal asymptotes. So there's no asymptotes for this graph. For symmetry, notice because you've got the x squared right there, that if you switch negative x for x here, you get the same equation. So we have y-axis symmetry, but no other symmetry. So next up, we look at increase-decrease. So we need to find f prime. So here's our original graph, and notice that's log of a function. So this inside function, x squared plus 4, we're going to call that our g of x. So if you differentiate the natural log of g of x, that formula is g prime over g. So the inside function goes on the bottom. So the x squared plus 4 goes on the bottom. And its derivative is 2x, and that goes on the top. And then we set that equals 0 here and try and solve. Those are the critical numbers when f prime equals 0. Well, the only way a fraction equals 0 is when the top is equal to 0. So that would mean 2x equals 0, so x equals 0. So here's our sign chart for f prime. 0 is our 1 cutoff here. I'm going to pick test numbers of -1 and 1. We're going to plug them into f prime. So plug a -1 in here. We get a 2 times -1, so a negative on the top. On the bottom, -1 squared is 1 plus 4, that's positive. Negative over positive is negative. Plug a 1 into f prime here. 2 times 1, positive on top. And then 1 squared plus 4, positive on the bottom. That is positive. So when f prime is negative, f is decreasing. When f prime is positive, f is increasing. So our function is decreasing here. So we are decreasing on negative infinity up to 0. And then we'll be increasing on 0 to infinity. And then notice that means that this has to be a minimum by the first derivative test. Function's decreasing, then increasing. This is bottom of a valley. So that minimum point is at 0. Well, we know what that point is. It's 0, 1.39 right there. So that's our minimum point. Next up, we need to analyze concavity. So for concavity, we need f double prime. So remember, here's our f prime. And notice that's a quotient, so we are going to have to use a quotient rule here. So let's call the top f and the bottom g. So for our quotient rule, we need to do f prime g minus fg prime over g squared. Right? F prime g minus fg prime over g squared. So derivative of the top, derivative 2x is just 2. Times the bottom, g is our bottom function, x squared plus 4. Minus the top, which is 2x, times g prime, which is the derivative of that bottom function, which is another 2x. And then over g squared, over the bottom squared, x squared plus 4 squared. And then we simplify here. So the 2 comes in times the x squared and times the 4. So 2 times x squared is that 2x squared. 2 times 4 is that 8 right there. And then we've got 2x times 2x is 4x squared. It's got a minus in front of it. So minus 4x squared. And bottom stays the same, x squared plus 4 squared. And then these guys are like terms, right? So you got 2x squared minus 4x squared is negative 2x squared and a positive 8. So 8 minus 2x squared. Bottom stays the same. We set that equals 0 to find the cutoffs for f double prime. Those are possible x coordinates of inflection points. Well, this fraction only equals 0 when the top is equal to 0. So I set 8 minus 2x squared equal to 0. So bring the negative 2x squared over as a positive. So 8 is 2x squared. Divide both sides by 2. So we get 4 equals x squared. Take square roots on both sides. X is plus or minus 2. So those are our cutoffs here for f double prime. And we want to tell what's going on with f. So let's pick some test numbers in each region. So for values less than negative 2, let's pick negative 3. For values between negative 2 and 2, let's pick 0. And for values greater than 2, let's pick positive 3. So now we plug into our simplified f double prime. If we put a negative 3 in there, this will be 8 minus 2 times negative 3 quantity squared. So 8 minus 2 times 9, it's going to be negative on top. And on the bottom, x squared plus 4 quantity squared. Well, anything squared is always positive. So negative over positive, that's negative. Plug a 0 in. Top, 8 minus 2 times 0 squared, that'll be 8. So positive on top. Bottom's always positive, so that's positive. Plug a 3 in. 8 minus 2 times 3 squared. Again, 8 minus 2 times 9, that's negative. Bottom's always positive. Quotient's negative. So we are going to be concave down. F double prime negative, that's concave down. F double prime positive, concave up. F double prime negative, concave down. So CCD, CCU, and then CCD. So what we know is that this function is concave down on negative infinity to negative 2. It is concave up on negative 2 to 2. And remember, you don't include the endpoints with concavity. And then concave down on 2 to infinity. 2 on out to infinity. So that means here concavity changed at negative 2 and 2. So we've got inflection points there. So we need to find those y coordinates, and x comma y will be an inflection point. So f of 2 and f of negative 2 are both the same. We go back to the original function to find those y coordinates, which is log of x squared plus 4. So whether you put 2 in here for x squared or negative 2, you get 4 when you square it, plus another 4 is 8. So those y coordinates are going to be log of 8. So both of those are ln of 8, which is about 2.08. So our inflection points are negative 2, 2.08, and positive 2, 2.08. So now let's put the pieces together and get a graph. So we are concave down here. We look up above and we're decreasing if you are to the left of 0. So decreasing concave down. So this piece actually looks like this. Decreasing concave down. Between -2 and 0, we're concave up. And we look up above, decreasing. So decreasing concave up. So in this region, graph looks like this. Between 0 and 2, we are concave up. Look up, we're increasing. So increasing concave up looks like that. X value is greater than 2, we're concave down. Look up, we're increasing. So increasing, concave down. Looks like that. So now we got to play dot to dot, put those things together. So let's go ahead and graph our inflection points. So -2, 2.08, about right there. And +2, 2.08, about right there. And then our minimum point was at 0, 1.39. So 0, 1.39, about right there. So let's go ahead and play connect the dots. So decreasing concave down, like that. Decreasing concave up there, coming into the minimum point. Increasing concave up, like that. And then increasing concave down, like that. And this keeps going up because there's no asymptotes. So there's a good sketch of our graph. And of course, you can double check this on your calculator.